In the example from the previous segment, we talked about comparing the returns of January to December. And the reason that we do this is because there's a financial theory or logic behind testing something like this, but there's a danger in just comparing two variables and seeing if there is a correlation coefficient. So for example, in this, if I thought, okay, so there isn't a correlation between December and January, what about January and February? What about February and March? What about February and July? I could test all of these over and over and over again and see if there is a correlation. But the risk that we have in doing that is what's called a family-wise or experimental-wise error. This is what's often called data mining. And when we data mine, or we take a lot of data and we just run it through a computer program that checks for correlation, that is common that we will find correlation coefficients that are significant, but it is just a type 1 error. In other words, we have found a significant correlation when really none existed. And that's why it's important that we recognize this family 1 or family-wise or experimental error. The way we calculate experimental error is by adjusting the alpha. So for example, if we had an alpha coefficient of 0.05 and we ran this test 3 times, so in this case C would be 3, or the number of independent comparisons. Well, our type 1 error increases from 5% to 14.3%. There's a 14.3% chance that we will find a statistically significant correlation coefficient when really none existed. So what's the lesson from this? The lesson from this is don't snoop. It's bad practice to print out as many analyses as possible and see which ones can be rejected or find which ones have a significant correlation. What we want to do is we want to plan the analysis first. We need to define the null hypothesis. It needs to be based in some theory, and then we can run the test. And if we run the test in that way, then we can be assured that the alpha, or the type 1 error that we would expect, is truly 5% or 1%. Let's move to an example where we are looking at various different correlation coefficients. In Excel, and explicitly in the data analysis tool pack, it allows us to do create a correlation matrix. When we capture many different variables, we can actually look at many different correlation coefficients at once. So in this example, we're looking at this survey that was done about Springdale Mall, and the data set is actually available in your is available to you in the data sets called Attitude. And what I've done here is I've simply just calculated a correlation matrix based on the data. We might as well open this up, so I'm going to open up the Attitude data set for you. And this wasn't the one that I wanted. There it is. So here we have a lot of different questions. So we have a question, what's your general attitude towards the mall? Do you feel like you can take your family to the mall? Does the mall provide variety of shopping experience? Is there convenience? Is it a convenient shopping mall? And then they ask some demographic questions about the gender. Now, it doesn't matter if zeros represent females or zeros represent ones at this point. All we're looking at is the correlation between these variables. We can see that we have about 200 people that were surveyed, And if we wanted to look at each individual correlation, we could look at the attitude versus take fam, attitude versus variety, attitude versus convenience, so on and so forth. The data analysis tool pack using the correlation allows us to look at all of these variables at once. So I'm going to actually highlight the entire data set, and it will create a correlation matrix. I do have labels. I want this to go in a new worksheet. And it'll create a correlation matrix that gives us the relationships between the two. Now I believe that this is the subset. Yes, it is. This is a subset of the data that was used in the example. So we ran through that to show you how that is done, but let's go back to this entire data set, not just a subset of 200 observations. So we can look at these different correlation coefficients, and we can say, okay, which ones are significant, which ones are not, which ones are positive, which ones are negative. What do we notice? So question number one, why are all the correlations on the diagonal 1? Well, we've talked about this before. This diagonal that we go through here are just the variables correlated with themselves. So they would, by definition, have a perfect positive correlation. Number two, why are there no correlations in the upper diagonal? Basically because the upper diagonal is just a mirror image of the lower left. So this value would be here, this value would be here, so on and so forth. Actually, that value would be there. So it's redundant. It's not necessary to put all of those different values because we would just see the same values. So let's examine the correlation matrix. Which correlations are significant at the 0.05? Now, the 0.05, given that we have a large data set, the R critical would be 0.139. Let me clean this up just a little bit. So we're looking for any correlation coefficients that are positive and greater than 0.139 or negative and less than 0.139. So we would have variety to attitude, variety to convenience, variety to gender or sex, and variety to convenience. Looking through there, I don't see any others. The take fam, this one right here is close, but it's not quite there. So how do we interpret the non-significant correlations, or what do these mean? Even though there's a correlation based on the hypothesis testing method, we can't say that that correlation is something other than 0. So even though this is very close to being significant, we'd have to assume that all of these correlation coefficients that do not meet our hypothesis testing criteria would actually be 0. And that's how we would interpret those. There really is no significant correlation. So let's interpret those correlations that are significant. Correlations between two quantitative variables. So quantitative variables would tell us something about the relationship. Correlations between qualitative variables or dichotomous variables tells us not as much information, but it tells us something also about the relationship, but is more difficult. We can't quantify that relationship. And we'll talk more about that when we get into regression. But what do we find here? Well, seems like the attitude and the variety. So when a customer sees that they have a high variety in products, they tend to have a higher attitude. When the customer sees that there is convenience, maybe the bathrooms are situated in the right places or they have different amenities, they also have a higher attitude. Doesn't appear that the gender really affects the attitude towards the mall. Both males as well as females might be equally satisfied or unsatisfied with the mall. We find that variety is correlated with convenience. So it seems like these two ideas of convenience and variety kind of go hand in hand, that the shopper really doesn't differentiate between variety and convenience. Now this is an interesting one. It says here that the variety is inversely related with sex. Now, I'm not sure, so we have zeros for females, 1 for males. So if we go from the females to the males, the variety component actually goes down. So on average, males rated the variety of this mall lower than the females did. That's what that negative sign is telling us there. So that's how we interpret these correlation coefficients and these correlation matrices. First, we want to know which ones are statistically significant. We ignore all of those that are not statistically significant because we have to assume that there is a zero correlation. Next, we look at the sign or the type of relationship, and we can make interpretations about the relationships based on those signs.